Well, thank you very much. It's a pleasure to be here. And I would like to particularly thank Akshat because he's helped guide me through the kind of topics that might be of interest to you. Most of the things I'll talk about today I have been interested in for many years. The topics that we'll see are not directly related to my own research. That would be more in the realm of supersymmetry and hyperbolic signal models, and that doesn't really fit very well with this audience. So, but the topics that I'll talk about are of course, they come from physics, and many of them we think we know the answers to, but we don't really know how, we don't really understand them the way we'd like to. So I will start with some basic things, which many of you may know or maybe know a little bit because you've heard about it. And the first thing I'll talk about is random walk. So these are the topics. These are the main topics of my of this lecture. It will be random walk or on ZD. So we'll describe some basic properties of random walk in D dimensions and its continuum limit on RD, on the wheels. And we'll see this is the basic. There are many questions that are still open here, believe it or not. But this has been studied for well over 100 years. And some of the progress has been made rather recently on random walk, and we'll discuss some of the new results there. So this is a very classical problem. Random walk goes, goes back to, doesn't go back to the Greeks. I don't think the Greeks believed in studying random walk, but it certainly goes back to the late 1800s and 1900s. Now, so that's a very classical question with still open problems, and I'll be describing them in the first part of my talk. The second part of my talk will be a problem which comes from quantum random dynamics. So I'm not really going to assume that you have a great familiarity with random dynamics, but this random pinball, which it turns out to be a special case of quantum dynamics, you don't really have to know much of anything. It's a very simple model on what's called a Manhattan grid, and I'll draw some pictures for you. And then there are various questions that one can naively ask about the trajectories of these paths. So that will be the second part of my talk, and it will have some connection with Brownian motion and random walk, but it will be a bit different. And as I said, it will be related to what's called quantum dynamics. There's the third topic. Well, as you know, I don't know when the elections come up here. Are elections coming up here soon in Cambridge or not? I'm a resident of USA, so we have elections coming up early November. So do you have them coming up soon or not? No. I've been getting some mail about registering for voting here, but of course I can't do that. So I thought maybe you had. But anyhow, this is a kind of a voter model, what we call majority rule model. So this is, in a way, unrelated to the first two topics. So if you get lost in what I'm saying here, this is a brand new topic, and I think fairly easy to understand. And now the last topic here is maybe a little bit more complicated. I'll describe it, and it's again related to quantum systems. And then it will come back to the theme of random walk. But these are random walks generated in a strange way, which I will try to describe during the last part of my talk. Now this last topic here is what's called edge reinforced walk, but I'm not going to get to it because this involves some kind of supersymmetry, and I think it gets a little bit heavy for this for an audience at this time of night. So let me begin with the random walk picture, and let me just say I'm very open to questions. This should be a very I like it to be interactive, And so we'll start with some very simple points here, and I'll make them a bit more precise. So random walk is sometimes called the Drunkards Walk because you imagine taking steps on streets or whatever you like, and the steps are taken independently without any thought. You don't remember what the step you took last time. So this is a very simple process, and we will denote the position after n steps as Wn. This is the walk after n steps, and it will belong to a lattice. So you can imagine that it's just the integers, or we go to 2 dimensions. We'll draw some pictures, and even in 3 dimensions. I won't try to draw pictures in 4 dimensions, but we will discuss 4 dimensions a little bit. So this has these walks. I'll be a little bit more precise about how they're defined, but they have a continuum limit. So you can take your lattice size and you can squeeze it down and let the walks run for a long time, and then you get a continuous path rather than just incremental steps. You have a continuous path, and that's called Brownian motion, and it plays a central role in, I would say, mathematics, physics, and especially finance, where it was, I think, really pioneered to some extent by people working in finance, and of course it's still a very active area. So the final thing I want to say is, in this particular slide, is that that these Brownian motions are continuous paths. We'll see pictures of them as best I can, but it has symmetries, which the other one doesn't have. For example, it's continuous, so you can ask what happens if I rotate the system a little bit. Do I see the same kind of path or not? And the statement is yes. You will have rotation invariant scaling law, and then there'll be a scaling law. I can scale my time by some parameter alpha, and then if alpha is big, that means I run my time a little faster. But then I have to decrease the amplitude here, and it will have the same law. So these are scaling laws, which of course play a huge role in physics, and you can't do them on the lattice so easily. But this is one of the big advantages of Brownian motion. So let me be more precise about random walk, and then we'll come to some problems, some open problems even, in Brownian motion. So by steps, so if you think about a random walk, you think about steps, random steps. And so if you're on the integer lattice, these steps you can go to the right or to the left, and you make them independent with probability half. So I have a 50-50 probability going right, 50-50 probability going left, and in Z2, you can imagine that my steps can go up, down, to the right or left by 1, or up and down by one step. And these would each be taken with probability a quarter. And my random walk, these are my steps, so my random walk after n steps, you just add these steps up, and you get a vector or a number in the integers, or in Z2, or in Z3 if you happen to be there. And so one of the basic properties of random walk is after n steps, you sort of wander around sort of aimlessly, but the distance that you go is after n steps is not proportional to n, it's proportional to the square root of n. Okay, this is a very small but important point, or the expectation of w squared is n, and the expectation of the path itself is 0. So you're equally likely to go up and down, or right and left. So this is easy, but this is one of the basic properties of random walk. The distance you travel after n steps is, generally speaking, proportional to the square root of n. Okay. So what does this mean? So this is a very simple thing. Many of you know it, of course, but I want to emphasize something, some features of it. So that means if I pick a big box in my lattice, pick a large box, and I look at the number of vertices or the lattice points I visited in a box of size L, it has a side of L, then the number of sites that I will visit is proportional to L squared. So that means I'll visit quite a few sites before I actually exit the box. And this -2 means I'm visiting a few less, a little bit less than 2, like L squared divided by log or log. But this is roughly the picture, and we'll see it in a minute. So we say that the random walk has a kind of dimension 2. It's not linearly in time, it's square in time, in the size of the box, rather. So we say that it has, and this will be true for Brownian motion too, it has a fractal dimension, which is 2. So now let me just continue a little bit more, and we'll see some pictures. So what are the basic properties of random walk? So one of the basic properties was proved, just 100 years ago, is that in 1 and 2 dimensions, the random walk wanders off, of course, because it goes a distance proportional to the square root of n, but in 1 and 2 dimensions, it comes back to where it started infinitely often. You let it run long enough, it goes further and further out, but eventually it always comes back. And this is what's called recurrence. And it's a special feature of 1 and 2 dimensions. So in a random walk, the particle may go very, very far away, but you wait long enough and it will come back. But that's the feature of recurrence. It's very special to 1 and 2 dimensions. In 3 dimensions, we say it's transient because with positive probability, it has a good chance of never coming back to where it started. It might come back a few times, and then eventually it will never come back. It will wander off, and that's what we call transit. It never returns to the origin. So here's a little statement. The probability after n steps that it comes back to the origin is proportional to n, the number of steps, and then there's a d over 2 here. So you'll see that's the summable if d is bigger than 2, but it's not if d is like 2 or 1. So that's a basic, very basic property which we'll see in other contexts. Okay, so here is a picture of, maybe it's not a very good one, at least with this resolution. This is the image of a random walk on a lattice, but maybe, I don't know how many steps this is, I've forgotten, maybe 5 or 10,000, I would say at least 1,000 steps. And notice that it starts to, there are holes here, of course, and there's some dark spots where it's really come back and visited again and again. And this is a typical walk, maybe after 10,000 or 5,000 steps. So it is we would say that it doesn't quite fill up area, but if I let the random walk here run for, let's say, 1,000,000 steps instead of 5,000, these holes would be filled up, and it would start to fill up this whole region here. They all look dark if I let it run long enough. It keep on coming back and back and back, and eventually that whole area would be filled up and look dark. So that's random walk in 2 dimensions, and so now I'll give you a picture about 3 dimensions where you can see it's quite different. Here's a 3-dimensional picture, and again, I don't know how many steps this guy has had, but you'll see that let's say this is a big box, it's got a lot of steps in it. So if this box is of size L, and I have L cubed vertices in it, this guy will visit, it doesn't really look like it here, but it should be visiting about L squared. So that should be visiting L squared vertices in a box of this size. And if I let the walk run for 1,000,000,000 steps, it will still look like this picture because the walks will have exited and never come back. So that is the difference, sort of visual difference you can see between transients and recurrence. Recurrence was in 2 dimensions. So let me just stop for a second and just see whether you should feel free to ask questions if something's not clear about random walk. I imagine many of you have seen some of it before, but pretty soon I'll be telling you some things that you probably haven't seen before. So let's just pause for a second here to see if anybody's got any questions. Yeah.
What happens to a random walk in a centillion dimensions?
In the centillion dimensions. Well, probably in the centillion dimensions, the random walk will still have all these properties that I mentioned, but it certainly will never come back. I mean, it's very unlikely to come back. And it will look like a self-avoiding walk. It would be very unlikely to come back at all. It would ever be very unlikely for it to cross itself at all. Okay. So it looks a bit different. And of course I can't visualize it in this way, because I can do at most 3 dimensions. Yeah, I think I have a question, yeah.
So related to that, does the explanation of the random walk visiting about L-squared vertices apply in any arbitrary number of dimensions?
That's right. That's correct. In any number of dimensions. Above 2. Of course, in 1 dimension, it can only go in 1 dimension. But yes. So the number of sites that this guy has visited, this is L squared, should be L squared here, and I have an L cubed box. L cubed box. Yeah. So that's, these are good questions, and if let me go on a little bit more, and you may have more questions. So Brownian motion is a continuum limit. That means I rescale my lattice so things get smaller and smaller. See, if you go back to look at these pictures for just a moment, you can imagine this being a curve, a pretty rough curve, but a curve passing through all these things, which is actually continuous. So if I shrunk my lattice so it became, instead of a lattice R3, then you can imagine what a Brownian path looks like, actually. So it's a little bit different, I should say, from random walk, but not too much different. For those of you who know, so what I will just say is that it is a kind of limit, as you take a large number of steps, but then you rescale space so that the amplitude of this thing goes down. And in the limit, as n goes to infinity, it means I'm running the thing for a large number of steps, but scaling it down, I will get Brownian motion at time t, where this is a real number. And this will now be, not just on the lattice, it will be a vector in the limit, it will be a vector in the continuum. And these guys are Gaussian, it means they're normal distributions, they have independent increments, like independent steps. And one thing I want you to notice is it has very much the same properties as random walk, except it's continuous. But notice that if you think about it as a path, if this were a smooth function, t1 minus t2 would be proportional to the distance between t1 minus t2. Here it's t1 minus t2 to the half power. That half means the function is very rough. It's not a continuous function at all. It's what's called Hilbert a half because of this exponent. And so that just goes back to the idea that the Brownian motion, even though it's continuous, when you think of it as a curve, it's a very rough curve, and its fractal dimension is also 2. So I won't be too much more precise about that unless you really want me to. So here starts to be some of the first interesting properties of random walk and how they relate to things that are maybe not so trivial, and maybe you don't know. So there's a theorem by Kakutami in the 40s that say if I take a Brownian path, so you notice the random walk intersected itself many, many times, right? But in the limit, this Brownian path does not intersect itself. It just has no intersections in 4 dimensions. And if I take 2 Brownian paths, and I run them independently, and I ask, do they cross? The answer is, with probability 1, they never cross. Okay? The 2 Brownian paths do not cross. Now that's not true if I take random walks. They will cross. So the scaling has some effect on the structure. They're quite similar, but there is this important distinction. So this is a fact that goes back into the 40s. Now I'm going to talk about something that many of you may have heard of and know, and that is you may have known about the theory of gases, where you have particles, and the particles interact when they collide, for example, and when they touch each other, or if they don't, maybe they just pass through each other. In ideal gases, the particles don't really see each other; they just sort of, just go through each other, and that's what you learn about. But for example, in quantum field theory, you don't have to really know what these are, but these are quantum field theories that have been studied in usually graduate work, of quartic field theories, and they can be expressed as a gas, like an ideal gas of Brownian loops. But these loops, so think of the loops as being particles, And these particles really only interact when they cross, when their trajectories actually meet each other. And now this theorem of Kakutani, which is pretty old, tells us that in 4 dimensions, these Brownian paths don't cross. They never cross. So this is, I mean, it's kind of strange that in 4 dimensions, these field theories, which physicists study, you read about it in courses, but by themselves, they're trivial. In other words, they're a free gas of Brownian loops. They don't interact. And this is a rather striking statement. But you can see it. You can see it just by thinking about these things as gases. Yes.
Sorry, what's the difference between a Brownian loop and a Brownian path?
Well, you can just imagine the Brownian loops are conditioned to come back at some point. But apart from that, they look like a Brownian. Just think of them as being Brownian paths, or a family of them. But actually, technically, there are loops. So yes. But you can think of them as they still have the same Hausdorff dimension and all that. So the idea is the Hausdorff dimension of these guys is strictly less than 4. So if I take two things whose dimension is less than 4, and I ask if they intersect, well, generically they're not going to intersect. Right? However, in 3 dimensions they will intersect because these are 2-dimensional objects. I take two 2-dimensional objects and I ask, will they cross? Yes, they will cross in 3 dimensions. So if I take two planes, they're generically going to cross, but not for 4 dimensions. So we expect there's no effective interaction, and this something similar for this 5-6 interaction. And so this is maybe a bit technical, but let me just say that there are theorems that work very much along this lines. One of them is due to Eisenman and Fröhlich. It tells you that in 4 dimensions, these theories, which you think maybe are interacting, do not interact. They are trivial theories. They have in the limit, they have trivial S-matrix. So that's a little surprising because when you do perturbation theory, you think it's not trivial. But in the limit, when you take the cutoffs to 0, this is what's going to happen. So in 3 dimensions, this is not true because the loops actually intersect, and a quartic interaction in 3 dimensions is an interacting gas, and you have things like Ising models and so forth, which are quite non-trivial, but in 4 dimensions, the statement is, from this perspective, you can see very geometrically that there's no interaction. So, of course, you can say, well, what about gauge theories? Well, gauge theories are different. They don't fall into this category, and you can couple these guys to gauge theories, and they will interact, but by themselves, they don't. Yes?
Is that related to the of the fact that mean field theory?
Yes, that's exactly related to mean field theory. It tells you that mean field theory at 4 dimensions is what's going on. Correct. Yes. Any other comments or questions about this? Now, I'm going to tell you something about 2 dimensions. I think that's my next slide. Yes. Okay, so here's 2 dimensions. And now I'm going to ask a very simple... So this is relatively recent work. This goes back to work in 2000. Kakutani, 1940. So if I ask, let's say I take 2 Brownian paths, or 2 random walks, it's the same. In this particular case, you don't have to make a distinction. Take 2 random walks, and you ask for the probability that their paths don't cross up to time n. So here's one random walk in the plane, or on Z2, and here's another one, and I'm asking that the probability that this path never crosses its independent path over here. So we know that has to go to 0 because these are 2-dimensional objects, they're going to cross. But now I ask for the probability that they do not cross. And then this probability is proportional to n to the 5/8. So this is not something that I think, something that Mandelbrot might have guessed, but because it's a fractal, we're talking about the fractal structure of Brownian motion. But this 5/8 is a rigorous exponent that was obtained by Waller, Schramm, and Werner using ideas of conformal invariance. In fact, they developed a whole theory of geometric Brownian motion applied to critical phenomena like Ising, and percolation, and so forth, which is quite different from other things that physicists had developed in the past. And so this is the probability that 2 two paths which are running around never cross. Okay? So it's got to go to 0, but it tells you exactly how it goes to 0 with this 5-weight slope. Okay? This is a non-trivial statement. So now they do something else here. So here I also tell you that this random walk picture is used to describe conformal field theory and so forth. So there's a whole area of mathematics and physics connected to these kinds of questions. So here's another picture for you. Here is my random walk. Okay. You can see it's about 2-dimensional, a little bit less than 2 dimensions. This is you can see it's filling up a lot of space. And now over here in this picture, what I've done is I've looked at the outer boundary of this walk. So I've erased anything that's sort of inside. So these are like the little fjords that you get at the boundary of this random walk. So Mandelbrot had speculated that this curve here has a Hausdorff dimension or fractal dimension. It's not like a line. That would be fractal dimension 1. It's 4/3. 4/3. So it's rough, but not that rough. Not nearly as rough as the Brownian path. And so this is the theorem of this theory, and this is, roughly speaking, a self-avoiding walk. So this is just to show you that there are still interesting questions about random walk. So if I ask in 3 dimensions, so I forgot to mention this, in 3 dimensions, if I ask for 2 paths not to intersect after time n, there's no formula. We don't know how to get a formula for this. And this is related to what's called critical phenomena, and it's hard in 3 dimensions. It's possible in 2 because of various conformal invariants that are present. So now I think, unless there's, maybe I should pause to see whether we have a question here. If not, I'll move on to something related but different. Yeah.
Do you know for certain that in 3 dimensions there is no exact formula, or is it?
Well, it's not known to me, and it's not known to anybody I know. So there may be one, and if you want to, in 3 dimensions, if you want to compute the probability that these 2 paths don't cross, you could ask your computer to run around 2 random walks, and then try to figure out what the answer is. I don't even know what the answer is supposed to be, but I doubt that it has a nice answer like this. I mean, it may be some transcendental number. We don't know how it goes. Yeah.
What happens if we project the random walk in like n dimension to n minus 1 dimension?
If I take a random walk in n dimensions, it said it will really, if I project it down from a high dimension to a low dimension, you mean?
Yes.
Yeah, it will start to fill up stuff. Yeah, it will be different. It will be different. Because if I take a projection, then I suppose I will get something different. So I don't think you can go from here to here at all. I mean, this is very much like what people want to understand in bootstrapping normalization. I mean, for those of you who know the terminology, you can compute things in 3 dimensions. This is probably one of the easier questions to ask, but there's no formula. It'd be interesting to find an algorithm for doing this, but it's not known. So if you don't mind, I will now move on to something else, which is my pinball. Okay. So this is a model. Again, you don't even have to know what I said before. These are separate pieces of the talk. There will be some connection, but so this is motivated by quantum mechanics, but you're hardly going to see any quantum mechanics in it. I mean, I will allude to it a little bit later. And this is called Chalker's network model of the integer quantum hole. So you don't have to know anything about that. But I will describe the parts. I'm going to show you a picture. So we're on a Manhattan lattice. So let me just maybe go directly to the picture. Because the picture tells everything. So before I go to the picture, let me just give proper credit. This model is made up by John Carty and his collaborators, and it was based on earlier work of, these are all physicists working in quantum Hall effect. Quantum Hall has to do with what happens when you have a system, a quantum system with a magnetic field pointing in, and you have random potential that sits around it. is still a very active area of physics and mathematics. There's many questions we still do not understand, but this is a model which you can understand, at least you can understand the dynamics of it, and I'm just giving credit here to the people who invented the model. It's an ingenious model. It's a very special model, though, so one shouldn't take it too seriously. So, I don't know, can you see these little tiny arrows that sit up here? Like this one points up, this one points down, this one points up, this one points from right to left, this one points from left to right. So these are oriented, this is an oriented lattice. For those of you who know Manhattan, this is what's called the Manhattan lattice because the streets are, roughly speaking, structured that way. You have alternating up and down and right and left. So there are little arrows here. I can see them, but can you see them? You can see them? Okay, good. All right. So this is a model. You don't have to know anything about quantum Hall or anything. You just imagine the following scenario: that you have this lattice. Of course, I've just shown you a finite piece of it, but you imagine it to be infinite or huge. And then you put down these little black dots. So it's like you're riding around in Manhattan. You want to go straight, and then you have an obstruction. These guys are what I call obstructions. And that means, so let's take an example here. I have a path here that comes in from the right, and it keeps on going and going and going. But you're traveling very happily along this way, and then you hit this obstruction. You cannot go through it, and you cannot turn to the, and you do not go back, and you cannot turn to the right here because the arrow, this is a one-way street. So once you hit this obstruction, you must follow the arrow, and there's only one way you can go. You go down, you keep on going, hit this other obstruction. You move this way because the arrow moves that way, and you move up, and so forth. So this is what I would call a trajectory starting from some edge. I just take the edge, I follow it till it hits the obstruction, I follow it till it hits the obstruction, and then eventually I might move out of my picture. So I could. Here's another one. See, these guys can cross, but they cannot share an edge. If they share an edge. Once you've got an edge, then you have to follow the rules of the road, and that determines your trajectory. Okay. So it's a very simple process, and what's important here is how these obstructions are placed, and we're going to assume they're placed randomly, independently on these vertices. Now, this is not a very good picture of random independence, because I don't have any vertices along here. But just imagine that I have some density of obstructions. Now, for those of you who know Anderson model, these you can imagine these to be random impurities in your system, and these are sort of quantum trajectories that would be followed. And the analogy is actually quite good, quite apt. So now let me just say what the story is. So if the probability of these obstructions is better than 50-50, then I get localization. And this is actually a theorem. And it means that all the trajectories that I should call these orbits, I should call these trajectories, they're all closed with probability 1. So that means if I look back at this picture for a second, this way, so that eventually, if these were more plentiful, I would have a theorem that says these orbits actually come back and form loops. They don't just go on forever. They do form loops, and they get and then so the way I've written it here, you think, well, they all just sort of run off somewhere, but for density bigger than half, they all get closed. That's the theorem. And the amazing theorem, the amazing conjecture made by Carty, is that all the trajectories are closed, no matter how dilute your scatterers are. That means all these guys that you think maybe are going off to infinity here are actually going to close. They're actually going to come back. Okay. So this is a conjecture. It's not a theorem. It's a conjecture for small p. And this is based on renormalisation group ideas, and so the statement is that they're close. It's easy to prove if p is bigger than a half. This is something that you can prove by showing that some percolating edges trap your particle. But for small p, we don't know what happens. And in fact, the loop diameter, the conjecture is all these paths eventually come back and form loops. But the loop diameter is huge. So you think maybe I could do numerical simulation to check this. And maybe you could. For p equals a half, easy. For p maybe a third, yeah, you could probably do it. But once you get down to about p equals a quarter, you cannot do the simulation reliably. Why? Because if this is accurate, it's beyond the size of your computer. Notice that if p is a quarter, that's e to the 16 power, and if I have a large coefficient on top of that, it's you can't run enough numerics to check it. So certainly for p equals a tenth, it's beyond probably around a quarter. I've been told it's very hard to check this, but there's interesting theory that tells you that this is the average loop diameter, and these are things that theory can tell you that your computer cannot tell you, because the computer isn't big enough to tell you when p gets, let's say, to be a third or a tenth or something small. It's just the lengths are too long. So this is an interesting problem. It's very much related to problems of localization in random Schrodinger, and maybe I'll review that for just a little bit, and you'll see the analogy of this problem with one that famously discussed by Phil Anderson, the Nobel laureate. And here is his model. You have a Hamiltonian, you have a quantum particle in the crystal. My particle is just a particle. There's quantum mechanics in what I wrote down. But the physics is very much the same. There's a quantum particle in a crystal in 2 dimensions, and there are random impurities, those are like my dots. So the random impurity is modeled by a random potential here. And this lambda here in red is important. It measures the strength of the impurity, or the density of the particles that you see, the density of the obstructions. And then when you want to solve the Schrodinger equation, which I've written down here, and I have an initial condition that says my wave function at the origin, my wave function at time 0 just sits at the origin, and I want to understand how it spreads out. I want to understand the time evolution of this particle. And so here's what happens. This is just conservation of probability. But if I ask how fast does it spread after a long time, then it can be bounded by a constant, that's localization. It could be diffusive, like a random walk, or it could be ballistic. So in 2D, this is a very famous paper of Abrams, Anderson, Cordello, and Krishnan, and they say that in 2 dimensions, that you always localize. This wave packet does not grow. It always gets reflected back. And that's very much like these loops. They always come back to where you were. And notice that the exponent that sits here, e to the minus, lambda to the minus 2. Now, if lambda is small, that means I have sparse scatterers, and that matches very, very closely with the predictions of Carty and this very simple Manhattan model. Now, I should say the Manhattan model is simple, but let me just make one very small point, which is, you see, I put these orientations in. If I don't have orientations and I put other kinds of scatterers in, what I'm saying is wrong. So this depends very much on the orientation. So maybe I'm about to embark on another topic which has to do with the voter model. So maybe one has some questions about localization and this Manhattan model. I'm free to, we have time to take a few questions. Yeah.
Sorry, what did you mean by, like, if you change the orientation?
Okay. So you see, I have an orientation here, right? All these guys have a different... I stagger these orientations. I have up, down. Suppose I decided to put 2 ups and then 2 downs. 2 ups. These are going to be different. Strangely enough, they're quite different. So it's very sensitive to the orientation. It doesn't look like it. You think it just has to do with scatters, and the orientation is just a decoration. It's not a decoration, it's essential. So that's what makes this problem quite hard, because you have to use the fact that you have this staggered orientation. It's not true otherwise. That's the point I'm trying to make. Yeah?
You said that the analogy to quantum paths in random Schrodinger between scatterers is apt. Why is that?
Well, because because remember in this problem, I claimed, and that was the claim of Carty and his collaborators, that all these paths will eventually close, and that they close with a loop diameter which is e to the p to the minus 2. Now if you put a lambda there to the minus 2, you would get exactly the same formula that was predicted by Anderson. Okay, so these obstructions are quite like, you shouldn't take it too seriously, but phenomenologically they're quite like a random impurity in a quantum system. In fact, this problem, let me just maybe make it a little bit clearer. This problem comes from quantum mechanics. This is a problem that Carty and Chalker and other people developed precisely to understand a quantum network model with this order. It's what's called a random unitary evolution. So the one that Anderson looked at comes from a Schrodinger operator, and there are different energies. Here there's really only one energy I'm looking at, but I'm looking at a unitary evolution. And then this problem with the SU2 disorder turns out to be actually isomorphic to this pinball model. But it requires special types of disorder. So it's a special model of Anderson localization. It's a very special model. But in this case, there are no phases to worry about. It's all probabilistic. The phases disappear because you have SU2 disorder. You have the SU1 disorder, you can't do it anymore. And people would love to know how to do it, but they don't know how to do it. Yeah. So now I'm going to change topics. I have time to change topic at least one more time. And so, by the way, let me just, now that I have this before me, let me say, you see, so how does random walk come in here? Well, you see, this guy really starts to look a little bit like a random walk. And actually, all these trajectories will look somewhat like a random walk. And that random walk corresponds to what's called diffusion. But eventually, although it looks like random walk for a very long time, eventually it's not. It comes back and closes itself and forms a loop. So these loops look a little bit like random walks, but they're not. So that's roughly speaking the connection. And now let me go to another model. Here we are. Yes. Okay. I was asking about elections. So this is a model which really has nothing to do in a way with the other two, but it has to do with the effects of the noise. It has to do with the effects of error, random errors that you might make in a process. And it's ultimately a toy model, a baby model, but not so trivial, of what's called non-equilibrium statistical mechanics. So the rules, I'll show you lots of pictures, and you'll hopefully get a feeling for how this works. So this is what I call majority rule, and it should be called local majority rule with noise. So here's the situation. I'll first explain it on the slide, and then you'll see it much better in pictures as usual. So at every site on the lattice, let's say I have a one-dimensional lattice, I have a voter or a spin. And the spin is either up or down, and the voter is either saying yes for up and no for down and be good. So I just have a sequence of ups and downs on my lattice. Okay. Now I'm going to tell you that that's my initial condition. I'm going to make my initial condition all yes, all ups for most of this talk. So they'll all be yellows, all be yeses for most of the talk. But then, when you update, you look at yourself. Here you are at site J. You look at yourself at time t, You look at your neighbor to the right and your neighbor to the left, and then how do you vote? You have your own vote, but when you update your vote, you go to time t plus 1, and you just take the majority of yourself and your two nearest neighbors. So if I'm voting minus, no, and my neighbors, my two nearest neighbors are voting yes, then at the next step I vote yes. That's what you mean by majority vote. And on the other hand, if I'm voting no, my neighbor to over here is voting no, and this guy is voting yes, I vote no, because the majority is minus. Okay? And in 4 dimensions, you would do the same thing. You look at yourself and your 4 nearest neighbors, and you would simply vote according to the majority in your neighborhood. And you keep on voting and voting and voting. Or this is really a dynamical, very simple dynamical system. Now, this in itself would not be too interesting until we do the following thing. So we're going to introduce some errors. So a random error. And these will occur independently at every time step you do this, occur independently. And instead of voting with my neighbors, I vote just randomly. I just flip a coin and say, oh, I forgot what my neighbors did. I'm just going to vote. I'm just going to flip a coin, and I'm going to vote plus or minus 1 with probably half, with probably r over 2, sorry, where r is very small. That means I'm not following the rule. I'm making an error at rate r. Okay, a little error randomly done. So you might think, that's not going to affect anything very much. I have to put a little bit of noise in my system, and then I want to see what happens after we repeat the operation many times. So here's the picture. So what happens, so let's suppose I set my initial condition to be everybody's voting yes. So of course if I never had any noise, everybody's voting yes, so everybody's very happy. We're all voting the same way. Now we start to introduce a small amount of noise. And we'll see what happens. Okay, so let me try to explain the picture. This is a time axis here. This is my initial condition, and everybody at the top here is voting yes. So these are, see, I can't quite read this. This is 255 time steps. Okay? And my noise here, or my error rate, is about 4%. Okay? And I made 255 steps. So at the beginning, everybody's voting yellow. Perfect. And you keep on voting that way. But then you see little errors creep in, the little red spots creep in because the errors have somehow combined to do something to make it bad. And so you think, that's not very serious, because after all, you see this guy's got a little red spot, but then majority vote eventually erases it, and so here it does too. But if you wait long enough, and guess what happens? The randomness beats the majority. So you have it down here. I will have an equal mixture of reds and pluses, and that's because of a small amount of noise. Now, if I made my noise even smaller, well, it might take longer for this to happen, but eventually, no matter how small my noise is, no matter how small my error rate is, the errors take over. They beat the dynamics. Now you see there's some order down here, because locally you order. So locally you're pretty red here, locally you're pretty yellow here. So there is some trace of what you have. So this is a non-trivial statement that no matter what you do, that you will eventually disorder. And you can ask yourself, well, can I make a rule, which is not majority rule, in which I will remember my initial condition? Because by the time I get down here, I don't know whether I started out with pluses or minuses. It's all the same. It looks the same after this time. The noise has wiped out everything. So that's the baby version of the problem. And now we go to 2 dimensions. In 2 dimensions, I start with so there's no time axis here. I can't draw a time axis because that would be a 3-dimensional picture. So this is a 2-dimensional picture, and my time, I started out with completely all yellows, and my time here is 1,000, and my noise here is about, I guess I have 6%. So you see, after 1,000 steps, I still have most of the yellow with a little bit of red thrown in because the error rates have come in. But they come in, and if you were to look at this for another 1,000 steps, these little spots would move around, but you would primarily see a yellow background with small amounts of error. So that's different. So 2 dimensions is different. And so now let's take a higher error rate. So this is what a higher error rate would look like. So before it was, I think, 6%, or I don't know. Now I moved up to 12% error, and my time is again 1,000. But you see, the errors are starting to collect, and you're starting to see evidence of the. So this is like a low temperature phase, and these are domain boundaries, and so that's what it looks like. So this one, I've gone up a little higher, but this is after 30 steps. I've only gone to 30 steps here. So it looks a little bit like the last picture, but now if I go up one more, so now it's starting, I've let it run a little longer time, same error rate, but a longer time. Now you see the presence of the errors is starting to take over, and eventually I will see a 50-50 background here of reds and yellows. So here's, this is at 60%. So there's some kind of transition that happens here. This is at time 1,000. And this should be more or less equal distribution of reds and yellows. And so if the error rate is too high, there's a threshold. If the error rate is too high, you forget where you started from. And this is very analogous to phase transition for those who know it in the Ising model, but it's a bit different. And so there are various questions we can ask about these systems. So this is, by the way, so let me tell you what the status. Maybe I should pause to see whether you have questions about these pictures, because they're fairly simple to understand, I think. But you may have missed something that I can help explain. Pictures explanatory?
Can this be done for centillion dimensions?
Centillion dimensions again. So, actually these problems are, in a way, easier in high dimensions. They're much better behaved in high dimensions. So many problems in mathematics or in statistical physics are much better behaved in high dimensions because there's less interaction. There's too much room for things to. So, for example, we learned that in 4 dimensions or 5 dimensions, these Brownian patterns never cross. Right? So if they never cross, not much happens. So it would be sort of similar to this, but it wouldn't be nearly as rich a structure. So high dimensions is somehow a little bit easier. In 4 dimensions, it's usually often a borderline between where things become easy and where they become hard. They become hard in 2 dimensions, in 3 dimensions, and easier in 5 and higher dimensions, generally speaking. So going up in dimension, you think that makes things complicated, but at some level, it makes things easier, actually. Yeah?
Having a larger cutoff in the majority would that make any difference in?
Sorry, would you say it again?
So the larger cutoff in the majority. So 1 year statement about like loop 2 or loop 3.
Oh, you mean range of the majority, or yeah? No, that's a very interesting question. I think it's all the same. But you're pointing to a very interesting question, which I will come to next, because you can ask, okay, the majority rule is a nice rule, but if I put on noise in 1 dimension, then eventually it overwhelms the majority rule. Not in 2 dimensions, but yes, I would expect it to be the same. Sorry.
What if you use Conway's game of life as an alternative to majority rule?
What's that?
If you use Conway's game of life.
Oh, Conway's game of life. Yes. Well, that's a much more interesting and more dynamic thing. That could be. That might be actually simpler in high dimensions too. I'm not sure. Low dimensions is not just good for visualizing. Things become become more interesting.
So Conway's game of life with noise,
Yes.
instead of majority rule with noise.
It's maybe a little bit like that, but it's different. I mean, Conway has more complicated rules, okay? And it's two-dimensional. Okay? But let me tell you something else. Okay, so let me get to this picture here, and then this is pretty much near the end of my talk. So. Okay, so here are some things that I want to point out, which are suggested by these slides. And so what we learned is in one dimension, the majority rule, or some other range. You could imagine a longer range, as was suggested. I'd look at range 3 or range 4 and ask what happens. I expect, I don't have any proof, but this very similar thing happens. So in one dimension, the majority rule becomes disordered, even with small noise after a long time. The initial condition is forgotten. So that means in one dimension, I can't do computation if I have errors. Because I put an input and I just get junk out. I always get a mixture out, so I haven't done any computation. So that's at least for long times. So here's a conjecture, which is in 2 dimensions, the order is preserved for small errors, but there's a phase transition. There's a critical threshold, which is about 0.16. I forget, maybe, I don't know exactly what it is. And then the long time correlations, and you can ask what things look like after a long time. So does it look like an Ising model? What is the structure? What does the configurations really look like after a long time? Is it like an Ising transition? So we're interested in long time behavior of some rules which you put in, which are maybe fairly simple. You add some noise and you want to understand. So this is what's called a non-equilibrium theory. You know the dynamics. Dynamics is simple, majority rule. You add some noise. Now, how do you describe the long-time statistical properties? Now, sometimes it's fairly easy. In this case, probably it isn't so difficult, but in other cases, it's extremely difficult. You don't have, it's a non-equilibrium theory, and you want to know how the time evolution behaves. So now here is the last, maybe the last point I would like to make, which is actually rather surprising and maybe even controversial. There's a guy, he's a computer scientist actually, at Boston University, and he says, okay, I'm not going to look at majority rule, that's not interesting for me. I'm going to look at a finite range rule. I'm going to make one up. I'm going to make a rule which is on one dimension, and I'll make a finite range rule. I don't want to take an infinite dimensional rule. I can do too many wild things with that. Let's take a finite range rule, and which will remember the initial condition. So in fact, depending upon my initial condition, if I run it a long, long time, I will get very different answers. So this says that there are infinitely many steady states that emerge, and they depend upon the initial condition. That means he's found an error-correcting code. That means his finite range rules have found a way of erasing the randomness which appeared in the system. So this kind of thing arises. He's a computer scientist. He knows how to handle, how to manage, maybe control error. And however, this proof is a highly complicated proof. And I would say maybe only Larry Gray has really, and the author himself, not Peter Gotch, claims to have understood how to make these rules to offset the noise. And so that you get, so you remember your initial condition. You don't remember everything about it, but you remember most of it. And so that your number of steady states that you get in the end are infinitely many, in fact, uncountably many in the infinite moment. So it's a very unusual process, not like anything that is known in ordinary statistical mechanics. So I have more material, but I see my time is up, and I think this is a good place to stop. So thank you very much.